Damas y caballeros, tengan todos ustedes muy buenas tardes. Bienvenidos al Salón de Grados de la Universidad Nacional de Córdoba, donde a partir de este momento damos inicio al acto en el cual se hará entrega del título de doctor honoris causa de esta casa al profesor doctor Omar Yaghi. Preside este acto la vicerrectora de la Universidad Nacional de Córdoba, Magíster Mariela Marquicio. La acompañan en el estrado el decano de la Facultad de Ciencias Químicas, doctor Marcelo Mariscal, la vicedecana de la Facultad, doctora Silvia Correa, el doctor Alejandro Fracaroli, integrante del Departamento de Química Orgánica de la Facultad de Ciencias Químicas y del Instituto de Investigación en Físico-Química de Córdoba. Se encuentran presentes la presidenta de la Academia Nacional de Ciencias, doctora Beatriz Caputo, integrantes del Honorable Consejo Superior y autoridades decanales de la Universidad Nacional de Córdoba, vicedecanas y vicedecanos e integrantes del Consejo Social Consultivo. Además, autoridades del gabinete rectoral y demás referentes de las distintas dependencias de la Universidad Nacional de Córdoba. Referentes de Office of Naval Research Global, ONRG, referentes e integrantes del CONICET Córdoba, autoridades y miembros de la Facultad de Ciencias Químicas y del INFIC, Instituto de Investigación de Físico-Química de Córdoba, referentes e investigadores del INIFTA, Instituto de Investigaciones Físico-Químicas Teóricas y Aplicadas de la Universidad Nacional de La Plata y del INTEQui, Instituto de Investigación en Tecnología Química de la Universidad de San Luis, docentes, investigadores, estudiantes, no docentes e invitados especiales. A continuación, el doctor Alejandro Fracaroli nos presenta a nuestro homenajeado.
Buenas tardes a todos. Gracias por venir. Estimada vicerrectora de la Universidad Nacional de Córdoba, Magíster Mariela Marquicio, señores decano y vicedecana de la Facultad de Ciencias Químicas, doctor Marcelo Mariscal y doctora Silvia Correa, señor director del Instituto de Investigaciones de Físico-Química de Córdoba, INFIC, doctor Sergio Dassi, señora presidenta de la Academia Nacional de Ciencias, doctora Beatriz Caputo, y demás autoridades y colegas aquí presentes. Hoy tengo el orgullo y el gran honor de presentarles al doctor Omar M. Yaghi, quien recibirá la distinción de doctor honoris causa por parte de nuestra Casa de Altos Estudios. Antes que nada, quisiera agradecer enormemente en nombre de nuestra unidad académica, la Facultad de Ciencias Químicas, y de nuestra unidad ejecutora de CONICET, del INFIC, a la Universidad Nacional de Córdoba por este reconocimiento que nos permite contar hoy con la distinguida visita de un científico de renombre mundial. El profesor Yaghi recibió su título de doctor en Química de la Universidad de Illinois en Urbana-Champaign en 1990, obteniendo el premio a la mejor tesis doctoral por el trabajo realizado. Luego realizó una estancia postdoctoral en Harvard con una beca de la National Science Foundation y en 1992 comenzó su carrera independiente en el Departamento de Química de la Universidad del Estado de Arizona, donde se convirtió en uno de los pioneros en el desarrollo de un nuevo tipo de materiales reticulares denominados entramados metalorgánicos o Metal Organic Frameworks, o MOF en inglés. Entre 2006 y 2011, su carrera académica continúa en la prestigiosa Universidad de California, Los Ángeles, UCLA, para luego mudarse en 2012 a la Universidad de California, Berkeley, y conjuntamente al Lawrence Berkeley National Laboratory, donde actualmente continúa su carrera ocupando las posiciones de James and Nettle Treter Chair Professor of Chemistry and Senior Faculty Scientist, respectivamente. El Dr. Yaghi ha realizado contribuciones fundamentales en el área de la química inorgánica que han impactado profundamente en el desarrollo interdisciplinario de dispositivos para la captura selectiva de gases de efecto invernadero, el almacenamiento de gas natural para vehículos y recientemente la recuperación de agua potable a partir de humedad ambiente, entre otras. Ha publicado más de 350 trabajos en revistas de alto impacto internacional, entre los que se destacan más de 100 artículos en el Journal of American Chemical Society, que tiene un índice de impacto mayor a 12, 26 artículos en la revista Science con un índice de impacto mayor a 42 y 8 en la revista Nature con un índice de impacto mayor a 43. Su índice H es de 176 y cuenta con más de 193.000 citas, incluyendo casi una decena de esos trabajos en los que ha sido citado más de 5.000 veces, según Scopus. Le han otorgado más de 50 patentes internacionales y en el año 2019 publicó además un libro titulado Introduction to Reticular Chemistry, Metal Organic Frameworks and Covalent Organic Frameworks, en la editorial de Wiley BCH, el cual constituye el primer libro de texto en el que se incluyen los conceptos básicos para el diseño, preparación y estudio de aplicaciones de los materiales reticulares porosos. Al Dr. Yaghi se le atribuye la creación de la nomenclatura Metal Organic Frameworks, la cual fue utilizada por primera vez en su trabajo publicado en la revista Nature en 1999, donde se describe la síntesis, caracterización y activación de MOF5. En 2005 informó en la revista Science el primer ejemplo de entramados covalentes orgánicos o Covalent Organic Frameworks, COFs, materiales cristalinos reticulares porosos compuestos enteramente por enlaces covalentes entre átomos de carbono, boro y oxígeno. Estos materiales y otros derivados diseñados y preparados en el laboratorio del Dr. Yaghi le han valido múltiples y prestigiosos premios internacionales, entre los que se destacan la medalla Albert Einstein del World Cultural Council en 2017, el Wolf Prize in Chemistry de Israel en 2018, el BBVA Frontiers of Knowledge Award in Basic Science de España en 2018 también, el Gregory Aminoff Prize de la Royal Swedish Academy of Sciences en 2019. Sumado a esto, ha sido reconocido como World Class Professor por el KAIST en Corea del Sur en 2009, como Doctor Honoris Causa por la Universidad de Putra, Malaysia, en 2017 y como profesor honorario de la Universidad de Tsinghua en China en 2022. Recientemente, en el 2020, la Royal Society of Chemistry le otorgó el Sustainable Water Award por sus contribuciones a la recuperación de agua potable a partir de la humedad ambiente en el desierto. Para resumir todas estas distinciones y más, basta decir que el Dr. Yaghi ocupa el lugar 22 en la lista de los top 1000 científicos y científicas de diversas áreas disciplinares más influyentes del mundo. Esta realizada por la plataforma research.com en el año anterior, 2023. Antes de agobiarlos con más datos curriculares y considerando que muchos de ellos están disponibles online, quisiera ocupar estos últimos minutos presentándoles al hombre detrás de estas distinciones. El profesor Yaghi, Omar, a quien tuve la oportunidad de conocer a través de una entrevista telefónica en 2009, y luego como investigador postdoctoral de su laboratorio entre el 2013 y 2016, es una persona extremadamente generosa intelectualmente, que supo motivar y enseñar a sus discípulos para trabajar con estos materiales reticulares, MOF, COFs, etc., aún sin tener ningún conocimiento o experiencia previa con ellos. A su vez, propiciaba permanentemente una mejor atmósfera de trabajo, invitándonos a humildes retiros de grupo, por ejemplo en Oahu o Maui, dos pequeñas islas en el estado de Hawái. Otro claro y marcado ejemplo de esta generosidad es el Global Science Institute, una iniciativa global que tiene por objeto colaborar altruistamente con grupos de investigación alrededor del mundo, posee 9 nodos en 8 países diferentes, para la resolución de desafíos universales, además de construir una cultura científica entre investigadores jóvenes de distintos orígenes y con distintos backgrounds. En el marco de esta iniciativa es que fuimos invitados al World Science Forum en el año 2017 para contar sobre esta experiencia, a la vez que países en desarrollo como Vietnam pudieron publicar sus primeros trabajos de investigación en revistas con índices de impacto mayor a 12. Eso fue por primera vez en su historia. El Laboratorio de Química Supramolecular y Sistemas Nanoestructurados del Departamento de Química Orgánica de la Facultad de Ciencias Químicas y del INFIC, con ICED, al que pertenezco, es un nodo parte de este Global Science Institute. Esto nos ha permitido estrechar lazos con la Universidad de California, Berkeley, y firmar en diciembre de 2016 un memorándum de entendimiento entre ambas instituciones, el cual fue rubricado por las entonces máximas autoridades de cada universidad, los rectores Nicholas Dirks y Hugo Yuri por la Universidad de California, Berkeley y la Universidad Nacional de Córdoba, respectivamente. Y tiene por objeto el desarrollo conjunto de programas de investigación, intercambio de recursos humanos y de materiales académicos. El profesor Yaghi ha demostrado verdadero liderazgo y creatividad en su carrera científica y ha servido de inspiración tanto para jóvenes investigadores como para colegas en todo el mundo, los cuales se han visto profundamente influenciados por su estilo y visión académica. Su generosidad y trabajo constante han permitido la rápida expansión de un nuevo campo de investigación, la química reticular, y el avance en el uso de estos materiales en más de 20 países de distintos continentes, entre los cuales, por supuesto, se encuentra la Argentina. Por todo ello, consideramos que reúne los méritos suficientes para hacerse merecedor del título Honoris Causa de nuestra Universidad Nacional de Córdoba. Los dejo entonces con el doctor Omar Yaghi, quien nos presentará los resultados recientes de su investigación, titulados La química reticular como solución al problema del cambio climático. Muchas gracias.
Muchas gracias por su presentación, doctor Alejandro Fracaroli. A continuación, invitamos a la vicerrectora de la Universidad Nacional de Córdoba, Magíster Mariela Marquicio, a realizar la entrega del diploma que acredita como doctor honoris causa de esta universidad al doctor Omar Yaghi. Por su parte, el señor decano de la Facultad de Ciencias Químicas procede a entregarle una medalla recordatoria de este momento. A continuación, vamos a solicitar a las autoridades que desciendan del estrado para escuchar las palabras del doctor Omar Yaghi y su conferencia titulada La química reticular como solución al problema del cambio climático.
Okay, thank you very much. I have an acceptance speech, but I think I'll skip that to have some time for the science. I want to thank all of you for being here. It's an honor, of course, to be honored in this way, in this magnificent place, and for me to meet all of you. And I want to thank the Institute of Chemistry, the Department of Chemistry, the Department of chemical sciences, as well as Professor Fraccaroli for his wonderful introduction. He gave me a translation, so I know exactly what he said. And so I am humbled by this occasion, and I want to thank all of you for it. This is about science, and it's about using science to solve the world's problems. So this is my lecture that I choose to talk about today. How do we use chemistry to solve the climate and the water problem fast? And what I mean by fast is that towards the end of my talk, you will see how we use AI to speed up the discovery and to speed up the everything around solving problems as vexing as the climate and the water problem. So let me just first start with the following slide. The ice caps are melting because of the Earth warming, the Earth atmosphere warming to 1.5 degrees already. And this is raising the ocean water. The fact that you have CO2 going into the water makes it more acidic. And so it is also harming marine animals, especially coral reefs. Almost half of the coral reef in Australia is already dead, and the other half is being seriously threatened. So we have a CO2 problem, and I won't go beyond that, but only to say that this CO2 problem is also altering our weather, and it's affecting the weather patterns. So it's affecting people's livelihoods, and as you saw in California recently, people's lives are as well threatened because of the damage that these severe storms bring about. The other problem I want to talk about is the water problem. So the New York Times had a very nice article, and in it they said a quarter of humanity faces a water crisis. Okay, by the year 2040, almost a quarter of the people living on our planet will face a water crisis. Not water stress, but water crisis. So that means that they will not have enough water to sustain themselves. And the red areas are the ones where you can see where this crisis is going to take place. So we have a problem, we have a water problem as well. And I think worse than that is that even in the areas where there is water, very often the water is not clean. Almost everybody in this room and any room of lecture always questions the quality of the water that they're getting in their kitchen. And this should not be the case. So those are two problems. Fortunately, I'm a chemist, and we know the source of the problem, and we know the source of the solution. Hydrogen is part of the solution. If we can store hydrogen at room temperature, we would have found basically a resource for energy that when it burns, it only produces water. Methane is being emitted into the atmosphere at an alarming rate, and it's worse than CO2 as a greenhouse gas. So we need ways of capturing methane from air. CO2 obviously is a big problem. We need to capture it from air as well. Even if we stop burning fossil fuels today, we still need to capture that CO2 in the air. And water. So the molecules that we need to be dealing with are small molecules, some of the smallest molecules we know in chemistry. Okay, but these molecules are very difficult to contain, very difficult to manage. So I'll show you. And whenever there's a problem in society, we go back to the periodic table. Okay? We need the periodic table more than ever. And chemists for the last 100 years have been linking atoms and molecules to make discrete objects like drug molecules or polymers. Okay? And I want to show you today how we can link molecules together to make materials. Okay? And the periodic table is at our disposal. So before I move away from this slide, I just want to say that I believe that any problem we face as a society is soluble, provided that society has the will to address the problem. Okay? So if we have the will as a society to solve a problem, we will solve it because of people like chemists who know how to navigate this periodic table. And today's story is especially like that. We started exactly like that. So back when I was a young independent researcher, back in '95, we discovered that there is a way to crystallize metal ions with charged organic linkers. And I emphasize charged because not only do you take advantage of the lone pair on oxygen to bind to cobalt, but also the charge-charge interaction makes for a very strong interaction. And so we figured out how to crystallize these back in the mid-1990s. And then, since the 1990s, we have developed chemistry that allows you to make a framework, but also modify its organic linkers, modify the metal oxide units, and let's see where this cursor is. Okay, I don't see it. But anyway, everything about that chemical structure could be modified. It could be expanded to make larger pores. It could be functionalized to alter the chemical environment of the pores. And so you can imagine that almost any organic molecule could be used as a building unit, and almost any metal in the periodic table could be used as part of these multi-metallic units that I'm showing here in blue. So we have already made about 100,000 structures, and the possibilities are endless. Okay, we have a library of organic molecules and the periodic table to play with, and already hundreds of applications are being pursued. Why? Because we have figured out a way of taking organic and inorganic, stitching them together through strong bonding interactions to make materials such as this one. This is called MOF5. We developed this back in 1999, and we use the yellow ball to indicate the space within which one can bind gases. So this has become a new branch of chemistry we call reticular chemistry, and we define it as the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. So we want building blocks so that we have some rational thinking behind making the materials. We want to use strong bonds so that when you make the material, you can put it in a power plant and keep it in a power plant for years, capturing CO2 and cycling CO2 in and out of the pores of the material. And we want them to be crystalline so that we can characterize them with definitiveness and know exactly where the atoms are and study their chemistry. So the result of reticular chemistry has been MOFs, COFs, these are the all-organic porous materials, and more recently, weaving. And for this, I do need to find my cursor.
So we can see the cursor here.
Oh, you can, okay, okay, thank you. See, you always need your students, okay? So we also discovered the first molecular weaving, which is to make threads that weave in and out of each other to make not just a porous material, but also a very flexible type of material. This is really a revolutionary material. We have reported on this now extensively for the last 5 years. I will not be able to talk about molecular weaving today, but the strong bond, the building block approach, is the key new aspect that encompasses the core of this reticular chemistry. So let's talk about solving the carbon dioxide problem. And this problem is divided into two parts: taking CO2 out of the air and also taking CO2 out of point sources like power plants. If a power plant burns natural gas, you have to take it out of 5% by volume of the flue gas. If you burn petroleum, it's 16%. The flue gas is 16% CO2. Okay, so we need materials that could accomplish binding CO2 out of sources. Okay, what are the minimum requirements for a carbon capture material? One is that you need high capacity. You need a material that takes in a lot of CO2 so that you don't have to do many cycles for that amount of CO2. You need high selectivity. You need the material to be functionalized in a way that can pluck out CO2 out of the air, leaving everything else behind. Otherwise, the other gases will occupy space inside your porous materials that will not be efficient. It needs to be water stable. It needs to be oxidatively stable. It needs to have cyclability. It needs to have low regeneration temperature, and it needs to be scalable to multi-ton scale. Okay? This is a tall order for a chemist. We can't just make the materials, but now we are obligated to making materials that are practical and can be deployed in society. The bad news is that there are a lot of materials, but none of them work. None of them really work. For example, aqueous amines, which is an old technology that is now being deployed for CO2 capture, is a problem because these amines are corrosive, they're toxic, and they create their own environmental issues. Carbon zeolite resins, you can see where these things fail. MOFs, as you'll see, it's complicated. The story of MOFs and carbon capture is complicated, as you'll see in a minute. But they are at least the ones that are now at the forefront of CO2 capture from flue gas of cement and petroleum, but not from air. Okay, so one of the MOFs, and I know that this is a MOF that's already being investigated here in the university by Alejandro's group. This MOF is amazing because it has sites within it, here within the pores, that could be functionalized with these amines. These amines are the green dots here. And so the structure is replete with these sites. It is these sites that are going to be plucking the CO2 out of the air. CO2 reacts with these amines, as you'll see shortly. In fact, on this slide, they react with CO2 to make, in the presence of water, make bicarbonate, or in the absence of water, making carbamate. Now, in the presence of water, you have the ratio of one amine binds one CO2, while in the absence of water, two amines for each CO2. So what I want to say is that this discovery that we can double the CO2 capacity in the presence of water, which is always present in combustion gas or in the air, means that we can have a 1-to-1 ratio between the amines that we functionalize the pores with and the CO2. And the ultimate test of whether your material is working or not comes from what we call breakthrough experiments, or by doing kinetic separation, where you have your material in a column, you expose it to air, and you look at what comes out and when it comes out. Okay? And in this case, you can see that this column captures the CO2 and leaves you with clean air. But this is the result. This is the data. So this is for MOF 808, the MOF I just showed you with the rotation. And instead of glycine, we have functionalized the pores with lysine. Lysine is more basic than glycine, so we anticipated that it would do better than glycine. And sure enough, the material over here is exposed to 400 ppm of CO2. That's how much CO2 is in the air. And immediately upon exposure of the material to CO2, the amount of CO2 drops down to zero. That means it sucked the CO2 out of the air and stays in there until the pores are filled, until all those amines have CO2 on them and saturated, and then CO2 breaks back out from the pores, okay? This area here is where the CO2 is retained in the pores. You've separated CO2 from air. That's what this says. And you've separated it from air, let's say right now in Cordoba, it's probably over 50% humidity, okay, with 1.2 millimole of CO2 per gram. Okay? For me to have a practical material, I need 1 millimole of CO2 per gram. So we actually beat the standard that is needed to commercialize this material. But we cycled this material. We cycled it 10 times. It was wonderful. 100 times, it was great. 200 times, very nice. 500 times, no. Because it's full of, although it's stable in water and acids, it's not stable in base. All those amines in the structure, just we could not sustain, the structure could not sustain that. So for CO2 from air, this material is not a good example, although it gives an inspiration that we can design a material that is able to do this. But we have not been asleep. Back in 2005, we invented the all-organic frameworks, covalent organic frameworks. Chemists said these could never be made, but we made them, we crystallized them. It's a long story. But nevertheless, if you look at the backbone, there are carbon-carbon bonds and carbon-nitrogen double bonds. Very strong bonds. Nothing will destroy this material. As you can see here, when we expose it to acid, 12 molar HCl, saturated KOH, the material is maintained. You can see the diffraction line. It stays crystalline. So this is a wonder. It's a wonder material. Okay? And so now we take onto that material, we can put the amine units and look at how much it's taking up. And from the first experiment we did, the direct air capture of CO2 is 0.3 millimole of CO2 per gram. That's dry without water. With water, this number doubles to 0.6 millimole per, and so we need to go to 1. But already for methane flue gas and coal flue gas, we're already in the commercialization stage. So are we able to bind CO2 from air using these materials? Yes. Okay. Are we able to achieve the capacity? Yes. And we're almost there with the CO2 capture. How about cycling? Okay, so we have been cycling, not this particular material, but a new material we made based on this cough. And it's cycling now up to 100 cycles. No problem. I don't anticipate a problem. Why would a material that has a backbone like this be destroyed? I already showed you that it's stable in all these conditions. So we think we have the answer to the CO2 problem. And when I go to the water problem, you can see that these materials are not boutique materials. They are real materials that you can make in multi-ton quantities. Okay, and so that's the fate of these coughs. They will be scaled up to those amounts. Already we have a blockbuster application for CO2 capture from cement flue gas. Cement flue gas, by the way, cement produces, I forget the exact number, almost 15% of the CO2 emitted in industry is emitted from making cement. So this MOF from one of my colleagues in Calgary, Canada, takes up 2 to 4 millimole of CO2 per gram at more than 450,000 cycles. This is already commercialized. This MOF will not work for air, but it will work for cement flue gas because it has higher CO2 amount. And already this is commercialized, and BASF last October came out with a news disclosure that they are scaling this up to hundreds of tons per year. Okay, so already MOFs are deployed in Canada, in cement plants, in several Canada plants to capture CO2 from flue gas. Okay, so I think chemistry is alive and well, and again, chemistry rises to the occasion of addressing the CO2 problem. We are at the beginning of it. You can already see BASF, which is the largest chemical company in the world, scaling up these MOFs. We've worked with them for over 15 years. They've scaled up almost a dozen MOFs to multi-ton quantities. In this particular case, this new MOF, they are now scaling it up to hundreds of tons per year to capture CO2 from cement plants. So I'm very happy about this development. Okay, let me now present the how we would like to solve the water problem. The red regions in the world are dry, okay? Even the frozen ones, of course, are dry. But our concern is with these regions, okay, where a lot of people live, but they're arid. And if I could make a MOF that works in the red regions, it should work everywhere in the world, even in areas of the world where there may be lots of water, but it's not clean. You can still use these MOFs to capture that water from the air. And so our vision is to have water from air anywhere in the world at any time of the year. And I think it's possible to achieve this vision because, first of all, water in the air is plentiful. We have almost 13,000 cubic kilometers of water in the air at any one time. And so if I was to give each one of you, each one on our planet, 50 liters a day, 50 liters of water a day, I would have only used a very tiny fraction of this number, less than 0.01% of the water in the air. So there's plenty of water in the air. I don't need to convince you here in Argentina because it looks like Buenos Aires and Córdoba are very humid places. So what's the difficulty in trapping trapping water from air? It's illustrated in this psychrometric chart. You have water vapor in the air in grams per cubic meter, plotted against temperature, and then here you have the humidity lines. Okay, and I've colored the humidified regions in green and the arid regions in brown. Okay, but let's imagine that I am in, I don't want to say Córdoba, let's say Córdoba, Spain, okay, or Granada, because it's a little bit drier there. And I'm at 30 degrees Celsius and 20% relative humidity. For me to take water out of that air, I have to cool down the air to 4 degrees Celsius, okay? I can get the water out, but I have to cool it down to 4 degrees Celsius. That's not very practical. Now, if I have a MOF that's programmed to take water out of arid air and compact it in the pore, and I take that MOF and I put it in a closed box and expose it to the sunlight, water will come out of the pores and condenses on the walls. Now I have harvested water. So, or I've created a box that has a humidity. So I've turned desert air into humid air or into tropical air, okay? So I've turned the air in Córdoba, Spain, into the air of Córdoba, Argentina. And that's the magic of the MOF. And so for me to take the water out of sea, which is the humidified, I only need to cool it down by a few degrees Celsius. Okay? That's it. And you were in my lab when we discovered this. Okay? And so, long story short, I'll give you the answer now. We created a MOF. We call it MOF 303. It's an aluminum MOF. And it has these rectangular pores. And if you are a molecule of water floating in the pore and you're looking around the walls of the material, you'll see this. You'll see hydrophilic sites. These are NH and N. This is perazolate. Hydrophilic and hydrophobic. Hydrophilic, hydrophobic. Avogadro's number worth of these in a mole of this material. And notice that in the isotherm, that this material takes up water at almost 5% relative humidity. Okay? And mostly at 10% relative humidity. And it releases it under very mild conditions. Okay, so, and it takes, basically for each gram of this material, you get 0.3 grams of water. Okay, so here's the, wait. Okay, let me go back. I have to say something here. This is what the material looks like. This is a single crystal X-ray diffraction, and I'm going to extract out one channel and slice it so that you can see exactly where the water molecules are. This is not simulation. This is real crystal structure where we figured out exactly the positions of every water molecule. Okay, so, oops, sorry. All right. Okay, let it play now. Now you'll see the water molecules going to the hydrophilic sites, okay? And then when the hydrophilic sites are saturated, you bridge over the hydrophobic sites. The hydrophobic sites repel water, while the hydrophilic sites attract water. This repulsion attraction allows you to modulate the strength of water binding, and therefore modulate the temperature at which you can release the water. So the water can be released from the system at less than 50 degrees Celsius because of that push-pull attraction, repulsion interaction. Okay, again, it took many years, and now we have a machine that deploys that MOF. And in this machine, you can see a door open where air goes in. The air goes into the MOF, and the MOF is heated. You can see the condensation there of the water coming out of the MOF. Then you'll see a puddle. The reason it's rotating is that you have more than one module of MOF. Here's a puddle of water resulting from this MOF. And then you can harvest from this machine about 5 liters of water a day. This machine is no bigger than, let's say, a microwave oven in your kitchen. And it deploys only 200 grams of MOF, okay? I want to repeat that. 200 grams of MOF give you 5 liters of water, and that 200 grams of MOF will stay in the machine for 6 years. And it has a lifetime of the electronics. Actually, it can operate longer than 6 years, but it's the electronics that fail, okay, that run the machine. To me, that's remarkable. You have 200 grams of MOF, and people always say, well, MOFs are expensive. And then when I ask them, well, how expensive are they? Can you tell me how much they cost? Nobody knows. But yet they still say they're expensive. Because they're new, we assume that they're expensive. They're not expensive. And if they are expensive, and I have an aluminum MOF, aluminum is cheap, dirt cheap. 200 grams that are going to stay in the machine for 6 years, it could be even gold. It's still cheap, okay? I think that's an important lesson, at least for the students. Not to ask how much, because if there is a market for what you're making, it will be cheap very quickly. And don't underestimate the innovations of humans, okay? So this is a very innovative solution that only uses 200 grams. And it's clean water. It's ultra clean.
Cheers.
Okay. It's distilled water, so it's not really as nice as Eugene is saying, but it's the cleanest water you'll ever get, okay? Because the pores themselves are a filter for water, and the water goes through several phase changes, and you have a very, very clean water. We tested it. It's all published. But we wanted to show that, in fact, this MOF can survive in its operation even in the harshest of deserts. And I know a neighboring country here has the Atacama Desert. We also have Death Valley. It's not as dry as the Atacama. It was a fairly dry place. And we have designed a system that uses pancakes of MOF to trap water, and it can trap water out of Death Valley's air. Now, this one is not electrified at all. In fact, it takes up the water from the air at night. During the day, it releases it by just exposure to sunlight, ambient sunlight. There's absolutely no energy being spent here, extra energy aside from ambient sunlight. Students like this because it ended up on the cover of Nature Water. Okay, so if anybody says to you chemistry is dead, you can tell them it's not dead, because I have a great example of how alive it is. I'll show you that example. Here's MOF 303 on the left. It takes up about 35 to 40% of its weight in water. Now, if I want to store more water, generally the answer would be for a particular chemist is expand the pores. But if you expand the pores beyond 20 angstroms, you start getting steps in your isotherm, and that does not lead to energy efficiency in terms of taking the water out. So you have to maintain with one step. To maintain one step, your pore size cannot exceed 20 angstroms. So how do I do it? How do I keep everything above MOF 303, because it's heaven given, and expand and just increase the surface, capacity? We added 2 carbon atoms. Now, to you, it doesn't look like much. But this took a lot of work, because we started with adding 5-membered rings, adding 6-membered rings. None of that worked, because it wedges itself into the pores, uses the pore volume. So the thin extender is the best. We call it long arm extension. This long arm extension, just the insertion of 2 carbon atoms, gives you 50% more water. 50% more people in that village can have water now. That's the power of chemistry. So when somebody says chemistry is dead, you can say, well, I think you're dead. So this is really an amazing, to me, I am always touched by how powerful chemistry is. And now we can take this material and show, in fact, it takes up 50% more water, it's cyclable, and it uses lower temperature to take the water out. Okay, so what does this mean? It means that if I don't use any electrical input, any energy input aside from sunlight, if I have 1 ton of MOFs, which is no larger than this table, I can give you 2,250 liters of water per day. And that MOF will be sitting there for 6 years, no maintenance necessary. No energy input aside from sunlight. Now, if you're impatient and you want more water in a shorter period of time, you can electrify it, and 1 ton of MOF will give you 25,000 liters of water per day. Day after day after day. No kidding, okay? BASF is already scaling up these to multi-ton quantities. And Eugene, the one that drank the water, he's still alive, and he is the CTO of a startup that we put together, and now he has a machine. This machine delivers 22 liters per day at less than 0.4 kilowatt hour per liter. I don't know what is the cost of electricity in Argentina, but in California, 1 kilowatt hour is about 7 cents. In Texas, it's 3 cents. 1 kilowatt hour. So now you can see that this is even less. This is 0.4. Okay, so this is 1.5 cents per liter. That's how much it's costing. It will cost you for each liter of water that you're getting. And this is only the first generation device. We haven't even begun to capture the heat that is emitted when you release the water. When we do that, that energy will be even lower than that. And believe me, if you don't have water, like some of the places where I come from, like these flags, okay, you don't care about plugging something in the wall and getting water, okay? But even when you plug it into the wall, we're at 1.5 cents, let's say if you're in Texas, for each liter of water. Okay, so I don't want to keep you too long, but I want to just 1 more minute to say that what I just showed you took 25 years. And there's no reason for us chemists to have to wait 25 years for our materials to reach society. So we should embark on embracing AI, developing what I call the digital innovation cycle. All of the stuff that I told you about is amenable to computation and can be used, AI could be deployed to speed it up. That's what I'm doing in my lab. We are using robotics, image recognition, we're building up big data, we're using machine learning to discover materials faster than before. Okay, much faster. And I'll just show you, instead of going through all my, by the way, just the power of the students, I know some students are here, the power of the students is to change the professor. We change you for sure, but you also change the professor. And I didn't even think that I would ever be doing AI in my lab or computation. But this student was trapped in China over the pandemic and was supposed to become a graduate student in my lab. And over the 1 year that we corresponded by Zoom, and during this time, he convinced me that AI could be a great benefit to our lab, and he started the first AI project in my lab. So I admire him. He has inspired me, as so many people, so many of my students. Okay, so then another student comes in. His name is Zach. This guy will never be defeated. This guy can solve every problem that you have. And so he introduced me to ChatGPT. Okay, and I thought, oh, this seems silly. It can't work for science. But in fact, I said to him, well, okay, try to get ChatGPT to tell us how to make a MOF. And it was very bad at it. But you could get ChatGPT to do a great job if you train ChatGPT on text mining, image mining, even becoming a supervisor, even molecular editing, even becoming a research group. I won't go through all of these, but I'll just show you the text mining. You can actually take the experimental section of MOF papers, and ChatGPT will tabulate for you exactly what starting materials you're using, solvent, blah, 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 all those things, and make a database out of it so that machine learning algorithms can now consult this database. Okay, and that, by the way, before ChatGPT, before you train ChatGPT, it wouldn't know what a BDC is, benzene dicarboxylate. And we chemists are notorious for referring to the same thing in 3 different ways. We can write chemical formulas, we can write abbreviation to chemical formulas, we can actually write text chemical formulas, so it's a disaster for ChatGPT, but you can train it, as Zach has done, to tabulate with 95% accuracy. Okay, we can also get ChatGPT to take image mining. So in many of our papers you saw gas uptake, isotherms. Well, it could take those isotherms and digitize them. Now you have a digital file of those isotherms that you can use for machine learning. And it will do this. By the way, the text mining, we did 220 papers in less than a week. ChatGPT in less than a week. How long would it take a lab to mine 220 papers for the experimental section? Well, first you have to recognize where the experimental section is, search for it, and everything like that. So this is quite transformative. ChatGPT Supervisor, we have developed a ChatGPT routine where a new student that comes into my lab wants to make MOF 808. Doesn't know where to start. Okay, ChatGPT will help you find the paper, instruct you on which starting materials you need, and if you get stuck in the middle of your synthesis, it will come in and tell you what things to try. Option 1, option 2, option 3, option 1, these are the things you can try. And in the end, if you're ambitious, you can get ChatGPT to tell you how to invent a whole new MOF. Okay, so if you are like me, doubtful about this, you need to be less doubtful, and we need to start experimenting more and more with AI, especially in this case with ChatGPT, because ChatGPT is going to make chemistry, doing research, much easier than it is now. So it will lower the barrier. We lowered the barrier with MOFs, because in MOFs you mix 2 things together, you get your MOF. Lower the barrier to research with MOFs. But now you can lower the barrier even further, so that a researcher in chemistry doesn't have to be a chemist. Okay, or those interested in chemistry, those who are interested in compounds in, I don't know, in a random country in the world, they don't have access to top-notch research facilities, can now plug into research. And if they happen to be experts, great. But if they happen to be people who want to make a compound to start a little industry in their local environment, they can do that. You don't need to be a chemist to do chemistry anymore. Okay? Leave that for the organic chemist. Okay, but we do not need to know chemistry to practice chemistry. Okay? So, and that can help us. Okay, research group. This one is amazing because as everybody who does MOFs know, it's difficult if you're a first-time MOF or COF researcher, even if you have been there for a while, it's always crystallinity is an issue. So you spend, for example, we wanted to make this MOF for water harvesting with a sulfur in it, okay? It would take a student 2 years to get there. But with ChatGPT or COF, here's a COF, how long would it take to crystallize this COF? Years. But with ChatGPT, we can, this is a group, it'll give you synthetic conditions, where to buy the equipment, 3D print the equipment, it programs a robot for you, it chooses the machine learning algorithm for you, it modifies the machine learning algorithm for you, and all of that, to give you conditions under which you can turn a material, as you see here, non-crystalline to crystalline. How long did it take this student to do that? Less than 2 weeks. Why do we need to suffer? Okay, students need not suffer. Okay, so that's the key. How long does it take us to fully activate the material to capitalize on its theoretical surface area? Sometimes years. Now you can do it in less than a week. Okay? All right, I can't go on because it's just, it also can choose for you different iterations on a linker and the cheapest sources of making that linker, as well as the easiest ways. Okay, my concluding remarks is that reticular chemistry create materials such as MOFs and COFs with atomic molecular precision. We are solving the climate and the water problem through chemistry, through reticular chemistry. And AI for reticular chemistry will lower the bar further for emerging scholars so that everyone can plug into science. And I think the third point is not trivial. I think we will be democratizing research, and this is an opportunity for chemistry. So finally, I want to acknowledge my wonderful students, the funding sources, and I want to thank you for your generosity and for this beautiful invitation, beautiful honor that you have given me. Thank you.
Agradecemos al flamante doctor honoris causa de la Universidad Nacional de Córdoba, doctor Omar Yaghi, por su presencia y su conferencia. Y agradecemos también la presencia de todos ustedes. Nos despedimos con los acordes del himno universitario Gaudeamus Igitur.